Alrighty, nerds. Back to transformations. Let's see how far we can get today. I only have 2 more days to get through this stuff, so I don't want to rush it, but kind of tired of transformations. I'm going to be real with you. Alrighty. First of all, I don't know why these words domain are written here, because we're talking about quadratics. And the quadratic domain is the same regardless of how you transform it. It's all real numbers. So shifting something up or down and reflecting it is not going to change the domain. Multiplying your x's by -2 doesn't change your domain. Multiplying your y's by none of your domains are changed, okay? So domain, all real numbers for all of these. What we're supposed to be doing is sketching the parent function and then sketching the transformed version of it. Cool. I'm going to go ahead and put the parent function on each one of these as a dotted y equals x squared. Cool? It's going to go through the origin, goes through 1, 1, because 1 squared is 1, and 2 squared is 4. So we're going to go through 2, 4. And since it is a quadratic, it is an even function. So whatever's on the right is on the left. And you might as well go ahead and throw that image on all 3 of these grids. So just go ahead and do that real quick. This is the parent squaring function. There. Okay. Yes?
Probably answered this yesterday, but how do you know it's an even or odd function?
I just know it's an even function because if I throw a negative x at this, the negative squared is going to be back to positive, which means nothing has changed. Definition of even is f of negative x equals f of x, meaning nothing changed. So drop in a negative x with parentheses around it, square it, you get back to positive x squared. It looks like nothing happened to the equation, so it's even. Cool. Time to do some transformations. This one multiplies your y values by -1. This one adds 2 to your y values. Or you could say, reflect it over the x-axis and then go up 2. So let's go to the dots that we put on there. Let's reflect them over the x-axis and then go up 2. So this dot right here, let's start at the vertex. If you reflect it over the x-axis, it doesn't go anywhere because it's on the x-axis. Now shift it up 2. It's here. This one, reflect it over the x-axis. Boop. Now shift it up 2. Landed here again. That means this is going to do the exact same thing. This one right here at 2, 4, if you reflect it over the x-axis, goes to 2, -4. Shift it up 2, 2, -2. Its reflection over here. This is g of x. There you go. So it's upside down and shift it up 2. All right. This is 2 horizontal transformations, the way it sits, right? The first one is reflection, a horizontal reflection. Reflect over the y-axis. Okay, I just did. See how nothing happened? Which is what I was just talking to Max about. Reflecting over the y-axis doesn't change this graph at all. So we can actually disregard that and then say, what does this do? Well, if you have a 1/2 on the inside, multiplying what by 2? The x values by 2. Yeah, that means the y values are going to stay the same, but the x value will double. So right here, this 1, 1, double the x value, it's a 2, 1. This one right here, a 2, 4, double the x value, a 4, 4. Doubling this x value changes nothing, and this graph is still symmetric around the y-axis. There it is. Interestingly enough, we could have, instead of ignoring the negative because reflecting this thing over the y-axis does nothing, what we could have done was what I was doing yesterday, and I could have separated those two objects that are inside the parentheses. Applied the exponent to both of them. But you know what negative 1/2 times negative 1/2 is? It's positive 1/4. So instead of doubling the x's like we did, we could have done this and then just divided our y values by 4. And watch what would have happened. This one right here, 1, 1 would have gone to 1, 1/4. Boop. This one right here would have gone from 2, 4 to 2, 1. Boop. Right there. So it is the exact same graph. Which one's easier for you to do? Well, that's up to you to decide. But yeah, either reflecting over the x-axis or over the y-axis, which does nothing, and then doubling your x values, or apply the exponent and then just divide the y values by 4. Either one, you get that picture. And again, I said it a few times yesterday, the only reason why we were able to get away with that is because this thing's vertex was at the origin. It's the only reason why we could do that. This one. Oh, the inside of that's in a strange order, isn't it? Yes, it is. He says indeed. What makes the inside equal 0? 2. Comma the number to the far right, 0. This thing's vertex is at 2, 0. The number on the front is positive. That means it points up. So I have a graph at 2, 0 that points up. And it's going to be slightly shorter. That might be kind of difficult to think about though, right? If you want, well, let's just do that. We said 2 makes the inside equal 0, and there's no number to the far right, so our vertex is here at 2, 0. So if the vertex went from here to here, which way did it actually shift?
To the right.
We went to the right too. So all of the coordinates are going to have to behave the same way. All of the coordinates are going to have to shift to the right too. So that's an x change. So let's take this thing right here and shift it right too. Boop, boop. Would have been right there, correct? Then, what does this do to its y value? Divided by 2, which puts, oh crap, I pressed way too hard. I was not trying to press the pin down there.
Cooper, stop messing with me, bro.
Yeah, Cooper, stop messing with him. Save it for the locker room. All right. Its reflection then is right here. And this time I'll actually take the tip off. Take this point right here, shift it right to, boop, boop, and then cut its y value in half. So cut the y value from a 4 down to a 2, right here. Its reflection then is right here, and you're ready to draw your graph. Just like that. Ta-da! But Mr. M, it sure doesn't look like this doesn't look like it says to shift right to. You're right. It looks like a lot more stuff happened, doesn't it? Let me show you why we were allowed to do what we did. So let's just scratch the word domain off so you don't think that I'm writing the domain. I'm not doing anything with the 1/2. But I am factoring a -1 out of here, so now it says x minus 2. Factoring out a -1 will change the order of multiplication. Now, if you square the parentheses and you square the -1, when you square this -1, what are you going to get?
1.
Positive 1. So this thing will actually clean up to 1/2 times 1, which I don't need to write, x minus 2 squared. Now you can see, oh yeah, it's just been shifted right to. So why didn't we need to worry about this reflecting over the x-axis? Because y equals x squared is an even function. Reflecting over the y-axis, reflecting over the y-axis doesn't do anything to even functions. That's why that doesn't change anything. You guys cool with that? Yes, no, maybe so?
I would have much appreciated if you restated it.
So the way this is supposed to have been written, let's just say I wrote this in the right order. Let me do it a different color. the inside of these parentheses says this, negative x plus 2, correct?
Yeah.
So that's what the parentheses are supposed to say on the inside. Let's not, well, I'll write the 1/2, it's not doing anything. If you describe this using SADMAP, it says go left 2. So let's take our vertex and go left 2, right? Now that we're here, this says, oh, and then reflect that over the y-axis, which goes to right there. So what I was saying is, I don't have to worry about this go left and then reflect over the y-axis because this parent function is even. So reflecting it over the y-axis doesn't change the black dotted graph. And that's why you're allowed to factor it out, square it away, and notice that it actually doesn't do anything. Tell you what, just factor out the -1, square it away, and then graph the way you know you're supposed to. Okay? Alrighty. For this one, what we're going to do is we're going to fill out this table from this image right here. We need to know what the y values are at each of these x values. Now at -2.5, you're about here, and come down, estimate that to be like -6. I'd say that's around -6 at -2.5. At -2, you can see you're at y equals 0. At -1, you can see it's right there at y equals 5. At 0, you're here at y equals 4. At 1, x equals 1, you're back at the x-axis, so y is 0. 2, down here at -4. 3, down here at -5. 4 back to 0, and 4.5 is once again up here at 6. There. We have coordinates for this picture. What we've been asked to do is sketch each of these transformations of this thing. And the way we're going to do that is by manipulating the correct x or y in the way that it's showing us to. For this one, the negative sign, is it inside or outside? Outside. So does this change x's or y's? Y's. All it's telling you to do is multiply your y's by -1. That means all of the x's are unaffected, and all of these numbers, we'll just multiply them by -1. So I'll be at -2.5 comma +6. -2 comma 0. Multiply by -1 doesn't change anything. -1 comma -5. 0 comma -4. 2 comma +4, because, you know, multiplying two negatives gets you a positive. So 2 comma 4. 3 comma 5 for the same reason. 4 comma 0, multiplying 0 by -1 doesn't change anything. And 4.5 comma -6. Now connect your dots and try to make it look like that. There you go, something like that. So what did we actually do? Oh, I missed a dot, didn't I? Sure as heck did. I forgot to do 1 comma 0. Oops. I skipped right over that one for some reason. Anyway, all we did was turn it upside down. We reflected over the x-axis. So it's that image just turned upside down. This one's not a true transformation. But we might as well do it because it's fun. What is this telling us to do? Well, it's outside, so what's it telling you to do? Yeah, it just says make all the y values positive. So if the y is already positive, it stays positive. If the y is negative, it becomes positive. So -2.5 comma +6. -2 comma 0. -1 comma 5. 0, 4. If I put my finger on it, I won't forget to actually do it. 1, 0. 2, make that 4 positive. 2, 4. 3, 5. 4, 0. 4.5, 6. So it's going to look like a bouncing ball. It's going to do this. Essentially, all it did was it took any parts that were below the x-axis and then flipped them up. That's all it does. This part flips up, boop, and this little loop thing flips up, boop. That's it. Not a true transformation, but you can do it. Now this one, we had a negative sign on the outside. This made us multiply our y values by -1. For this one, the negative sign is on the inside. So you get to multiply the x values by -1. Now you can't see these on my screen while I'm doing this, so you'll just have to look at your own paper and trust that I am changing the sign on the x values. So it's going to be positive 2.5, comma -6. Positive 2, 0. Positive 1, 5. 0, 4. -1, 0. -2, -4. -3, -5. -4, 0. -4.5, 6. It looks very similar to the orange one, but you can see they're not the same. This one was our original graph upside down, reflect over the x-axis. This one is our original graph backwards, reflect over the y-axis. How can I tell the difference just by looking? If I didn't see this, how could I tell the difference? Because you can look at the points that didn't move. These 3 zeros are still zeros here. They didn't move. That tells me anything on the x-axis didn't move, so I must have been reflecting over the x-axis.
I thought they did. They're
Not-
on different x points.
Not the orange ones. I'm talking about the orange ones.
Oh.
So that's how I know that this is reflect over the x, because things on the x didn't move. Whereas this one, things on the y didn't move. So that's how I know I reflected over the y-axis, because it is different x's now. Okay, I'm running out of colors. Maybe I'll break out ye olde yellow. Yeah, at least it makes Amberly happy. What is this telling me to do to my x's? It looks like divide by 2, so this means double your x's. Man, it's hard to see. Does it show up on the camera okay? Yeek. That's tough. Yeah, it's tough for my eyes. It's hard for me to see it. We have to double all the x values. Again, you can't see them. You'll just have to trust that I'm actually doubling them. But don't touch the y values. So instead of -2.5, comma -6, I'm at -5, -6. Instead of -2, 0, I'm at -4, 0. Instead of -1, 5, I'm at -2, 5. Multiplying 0 by 2 still gets you 0. So 0, 4, unaffected. Instead of 1, 0, I'm at 2, 0. Instead of 2, negative 4, I'm at 4, negative 4. Instead of 3, negative 5, I'm at 6, negative 5. And the last one's going to fit on the grid. Instead of 4, 0, I'm at 8, 0. The other one comes off the grid, goes to 9, 6. But my grid doesn't go to 9. So we try to connect our dots now. Oh, I missed one. Crap. Get on that dot. There we go. Close enough. What did we do? Horizontal dilation, factor 2. That's what we did. Notice the only coordinate that didn't move. Which one is it? 0, 4. The only coordinate that didn't move was the y-intercept. Why is that the case? Because a horizontal dilation is literally taking a graph's points and moving them either closer or further away from the y-axis. Since this was on the y-axis, doubling its value of x still gives you back 0. Now this one, I'll use purple. It's going to look like black a little bit. This one looks like you're doubling your x's, so you're not. So I'm tired of drawing these things because I think we get it by now. This one is divide the x values by 2, or multiply the x's by 1/2. What is that going to look like? It's going to be a skinnier graph because you're multiplying by 1/2. This looks like we're subtracting 1 from x, so what are we actually doing? Adding 1 to x. But what does that do? What kind of transformation is that? If you add 1 to your x values, what are you doing? Horizontal translation, and since we're going to the right, would I say 1 or negative 1? 1. So horizontal translation, one unit. And we all know, hopefully, that means to the right. So that would just shift the graph to the right. I'm just kind of tired of drawing them. Plus I'm out of colors. What do you think about those? Not too bad if you've got a table of data to transform it? Yeah. Yeah. Okay. All right. Next. Boop. Finally, transformations of rational functions. And we've already graphed rational functions this year. We did it a bunch. But we didn't talk about rational functions through the eyes of transformations. As long as they are linear, notice all of these are, none of them have a degree 2 anywhere. As long as they're linear and written in standard form, all of these are written in standard form, darn near standard form, but don't worry about it. They're very easy to graph. What we're talking about here is the graph of y equals 1 over x and its transformations. This is the parent reciprocal function. It has a vertical asymptote that is the y-axis. It has a horizontal asymptote that is the x-axis. And it looks like this. That's just its look. Shifting left and right will shift this vertical asymptote left or right. Shifting up and down will shift this horizontal asymptote up and down. This is an odd function. So reflecting it over the x-axis is exactly the same thing as reflecting it over the y-axis. Either one of the reflections would put the curves here and here. So if you do both reflections, it changes nothing. Okay? All right. Standard form of a reciprocal function, standard form of a rational function that is linear, looks like this. Where do I want to fit it? Just like that. This is the quote-unquote inside, because this is where the x's are. The inside is always where the x's are. So this is you shifting left and right. What that means is, whatever the shift value, the horizontal shift value is, that is your new vertical asymptote, because it's supposed to be x equals 0. So if you shift it to the right 3, now it's at x equals 3. If you shift it left 1, now it's at x equals -1. This thing's horizontal asymptote is supposed to be y equals 0, the x-axis. So if you shift it up or down, you have shifted where the horizontal asymptote is. Net result is this number out here will be your horizontal asymptote. So your vertical asymptote is found from how the shift is here. Your horizontal asymptote, vertical is found here. Horizontal asymptote is found from this shift. So then, Mr. M, what does this handle? This handles the reflections if there are reflections, and it would also be our vertical stretch or shrink. Mr. M, I noticed that you did not mention horizontal stretch and shrink. Well, that's because there's a way to manipulate things. Just like with quadratics and cubics, you don't have to write this. You snatch someone's pass out of the trash. You could say that that is horizontal shrink factor 1/2, right? But this is exactly the same thing as saying this. And now it's a vertical shrink of factor 1/2. So because anytime there's a number in front of x, it could be factored and moved. And this is the same thing as saying this. All of our dilations of any kind can be addressed by moving them to the top. Will I do that? No. But that's why when we write it in standard form like this, there's not a letter sitting in front of x. It's because there is a way to manipulate it to get it out of there. So the standard form does not put a number in front of x. Anyway, let's go to it. First things first, it says state the domain. You're not allowed to divide by 0, right? So what is x not allowed to equal? -2. So this thing's domain is everything except for -2. Now let's talk transformations. There's supposed to be an x down here. Instead, there's an x plus 2. What kind of transformation is that? Shift left 2. That means your vertical asymptote, which was supposed to be at x equals 0, has moved over 2 to the left to x equals -2. Has my graph been shifted up or down? It has not been shifted up or down. That means my horizontal asymptote is still right where it should be at the x-axis, y equals 0. So we've got x equals -2 is our vertical asymptote. We've got y equals 0 is our horizontal asymptote. Has my graph been reflected at all? No, it hasn't. That means my two curves will still be top right, bottom left. They're still going to be here and here. Top right, bottom left of the asymptotes. We do need to try to find the intercepts, though. Let's start with the easy one. The easy intercept to find is always going to be your y-intercept. When you're on the y-axis, what does x equal? 0. So finding the y-intercept will always be very, very easy. You just let x equal 0. So let's figure out what f of 0 is. That's going to tell me where I cross the y-axis. It's 1 over 0 plus 2, which is, 1/2. This graph crosses the y-axis at positive 1/2. This is just a rough sketch. So I know it does this. There was no reflecting, so it didn't have a choice. Does this graph have an x-intercept? No, it does not. The reason why is because if you try to let y equal 0, which is how we would find x-intercepts. In fact, let's just try. Let's just try for funsies. What color do I want to do that in? I guess I'll do it in blue. Let's try to find our x-intercept. That means y equals 0. So you go, okay, well 0 equals 1 over x plus 2, and now you're trying to solve for x, right? You don't like fractions, I know you don't. So let's get rid of it by multiplying both sides by x plus 2. When you do that, x plus 2 times 0 is 0. And what's left on the right side is 1. Does 0 equal 1? No, it does not. So there is no x-intercept, because that is a false statement. So then how are we going to sketch that bottom curve? We're just going to say, there, that's good enough. It just needs to be a mirror image of that. Yeah.
Can you still plug in numbers?
You're welcome to plug in numbers if you like to. You don't need to, though. It's a sketch, not a graph. That's the difference between the two. A sketch just has the major pieces and then the general shape. So intercepts, asymptotes, and general shape, done. Good enough. Questions, comments, concerns on that? Anything I can explain better or differently or anything like that? No? Alrighty. Next. First things first is domain. You're not allowed to divide by 0. What makes the bottom equal 0? -1. So our domain is everything except for the number -1. You know why? Because that's the new vertical asymptote. Your graph has been shifted left 1. This is a horizontal translation of -1. Your new vertical asymptote is x equals -1. The graph has been shifted up 3. So your horizontal asymptote has moved up from y equals 0 to y equals 3. Did I do any reflecting?
Yeah.
Where? Is that a negative number? Negatives are reflections. So there are no reflections here. What that tells me is this graph will still look like this around its asymptotes because there was no reflecting. See, I used red asymptotes instead of axes because it doesn't matter where the axes are. This will be the behavior around the asymptotes because it was not reflected. Like I said before, finding the y-intercept is really, really easy. Anytime you want to find the y-intercept of any graph, you just let x equal 0. So let's figure out what g of 0 is. It's 2 over 0 plus 1 plus 3. That's 2 plus 3. Oh, that's 5. My y-intercept is at positive 5. I already know that this is the shape up there, so I'm going to go ahead and draw that in. Okay. This graph will have an x-intercept. How come? Because the horizontal asymptote is no longer the x-axis. That means this graph can now come into contact with the x-axis. Now I know it's over here somewhere because I know that this has to be over here. So it's going to be a number that's less than -1. But what is it? I don't know. Let's find out. When you're trying to find your x-intercept, you are letting y equal 0 and solving for x. So 0 equals 2 over x plus 1 plus 3. Now we need to solve for x. Subtract 3 from both sides. You don't like fractions? Okay, fine. Multiply both sides by x plus 1. Still trying to solve for x? Distribute the negative 3. I added 3 to both sides, then divide by negative 3. X equals negative 5 over 3, which is what? Negative 1.6 repeating? Did I do that math right? Yeah. That's almost negative 2. It's almost negative 2.
Okay.
It's like that. Ta-da! You found all the major pieces. The rest is just a rough sketch. Boom. What do you think about that? How about this? How does graphing rational functions using transformations compare to when you have x's on the top and bottom and you have to decide your horizontal asymptotes and all that stuff? Isn't it much better when they're in standard form? It's much better. You know, we always could have done this when we were doing our rational functions, as long as they were linear over linear. All you had to do was long division. Long division puts rational functions into standard form. This is the remainder, actually. This is the divisor. It would have gone in 3 times with a remainder of 2. Yeah. We did it in Algebra 2 last year. Okay, hold on. I see a negative. That means there's a reflection. Because there's a reflection, it will not be top right, bottom left. It'll be top left, bottom right. This is going to be the behavior of this graph. And I know that instantly because I see the reflection. Cool beans. Domain. What would make me divide by 0? What x value? 3. So x can't be 3. Because 3 is my new vertical asymptote. X equals 3 is a big fat no-no. My graph has been shifted up to. So my horizontal asymptote is going to be shifted up to from y equals 0 to y equals 2. We already know that it's going to be up here and down here. We just need to find our 2 intercepts and draw our curves on there. We're ready to rock and roll. As usual, finding that y-intercept is so stinking easy. You just let x equal 0. There we go. I can speak. So we get h of 0 equals negative 1 over 0 minus 3 plus 2. That's going to be negative 1 over negative 3. That's positive 1/3. 1/3 plus 2 is 2 1/3, or 2.3 repeating. Your y-intercept is at 2.3 repeating. Y-intercept. I did this wrong last period. So that's, wrong color. Here-ish. I already know that there's going to be a curve up there, especially because it went through that dot. So let's just... Oh, man, I missed it. Close enough. Now let's track down the x-intercept, which is always going to be a little bit more work. Letting y equal 0 and solving for x. Subtract 2 from both sides. Multiply both sides by the bottom of the fraction. Distributing negative 2 gets me negative 2x plus 6 equals negative 1. Subtracting 6 from both sides will get me negative 2x equals negative 7. And then dividing both sides by negative 2 will give me x equals positive 7 over 2, or positive 3.5. So here. And then there was 1. And that'll be the last thing that we get to do today. Oh no, horizontal crap. Don't worry about it. We weren't asked to describe the transformations. We were just asked to graph. Maybe this time it's a little bit harder to see what makes you divide by 0. So fine. Go ahead and figure out what would make this equal 0. Add 4 to both sides. Divide by 2. Okay, x equals 2 would make my denominator 0. So my domain then is everything except for x equals 2. Because that is actually my vertical asymptote. And it's been shifted down 3. So your horizontal asymptote is at y equals negative 3. I'm not pardoning his interruption.
Just want to announce that this evening the girls volleyball team has a district semifinal match.
There we go.
Tonight at 7 p.m.
There has been no reflecting. Since there's no reflecting, I know that around my asymptotes, my graph will look like this.
District semifinal matchup against Lehigh at 7 p.m. The first 100 students to get in for free.
Track down my y-intercept
We will leave at the bell.
by letting x equal 0. K of 0 gets me 1 over 0 minus 4 minus 3. That's negative 1/4 minus 3. That's negative 3.25. So down here. I mean, I already knew there was going to be a curve down there. Now I know where my y-intercept is. Just need to find that x-intercept and call it a day. This one's always going to be more work. So add 3 to both sides. Get 3 equals 1 over 2x minus 4. Multiply both sides by your denominator. Distribute. Add 12 to both sides. And divide. It's going to get you x equals 2.17-ish. It's actually 2.16 repeating, but that's really, really close to that asymptote. So your graph looks like this. Sheesh. We did it.